All right. Right. So does any of you have any question related to homework for number 1? Okay. Sounds like straightforward. How about problem number 2?
I think these are not that difficult, like once you understand like with the formulas. I think the only thing I'd say maybe is like the free body diagram. So
Okay.
when drawing each one of them, I get sometimes confused because if you look at the one you drew here, it
Mhm.
you drew theta going up, but I thought that
Absolutely.
theta goes with the direction of the theta. So
You are
what
right. So there's a typo here in this one. So there's a problem. So you are right. Theta should be going down. Okay, so it's something like this. And we have, let me take a screenshot from here. Right, so let's map the, so here we have R is going to be this way. Let me make this in a bigger outline. Let's make it this way. This is R. And since theta is going down, and how did I know that theta is going down? Because omega is turning this way. Since omega is this way, this the velocity, so definitely this arm is moving down. So this is R and theta. The tangent normal, since this is going down, let's make it in red. All right, so the tangent and the normal is perpendicular going down. So this is n. By the way, it's a very, very important to be able to map the coordinate system. And xc, as you read in the note, xc should be more than negative 90 degree and less than positive 90 degree. It's a sharp angle. It should be a sharp angle. If you look here, and xc is the angle between r and the r vector and the tangent vector. So this one is not a sharp angle. So xc should be between r, either r positive or r negative. So what we are gonna do, we are gonna extend the r negative, and it's gonna be this angle. So this is the xc angle. So once you get xc, which is the tan inverse r over dr d theta, so it is going to be this angle. And if you extend this line, so these angles are opposite, so they are equal. So this is going to be xc as well. And if you extend this angle and this angle is 90 degree, and this angle and this angle is 90 degrees, so this angle is xc as well. So it's a very, very important to know how to get the xc angle. There's different settings of the problem. Like there was a one in the recording that I sent to you last time that you have like a circular path and there's an arm like this, but the arm was like making 945 degree. So if this angle is 45 degree, and so this is R, and the theta, I'm not sure where the arm, maybe I believe was going this way. So this is gonna be theta, and the tangent in this case was something like this. I'm not sure the arm, let's assume that the arm was going to the other way. Mm. But anyway, it's the same. Like if you want to do it both ways, it's gonna give you the same thing. Like if this arm is going this way, so the tangent is gonna be this way, and definitely the normal is gonna be this way. So the angle between the tangent and the normal is this angle because it's the angle between T and R. And actually, it's a very simple in this case. I don't have to calculate it. Why? Because you have a line like this, and this line is 45 degree, which is this angle, and this is here. So this is equal 45 degree as well, the angle between them. Sometimes it's easy that you can predict it from the geometry, but sometimes if this arm is somewhere, for example, here, it's gonna be difficult. So you need to substitute in this formula. All right, so this is actually should be how how to get XC and how to map the axes. And actually, if you want to map the XY axis, so this is X and this is Y, and this angle is still theta. So this is I mapped the whole, the Cartesian, the polar, and the tangent normal coordinate system. All right.
Yeah. That looks about right. That looks really good. Thank you, Professor. Since we're still in like about polar coordinates, I was gonna ask you, I was looking over the lecture notes and my notes. You mentioned N and P, so I understand that the problem sometimes ha might include those, and that's when we have to include like the sum of forces equals mass times acceleration. I understand, but I'm not really sure how we draw N and P correctly. Because sometimes I feel like
Uh-huh.
I can't visualize it.
Absolutely. Yeah, we can do that. All right. So let's do it this way. Okay. So let's, for example, say that we have our arm here. This is our arm, like was at this position. Okay. So the P, the force that pushing an arm, like this arm as soon it's moving, so always the force is perpendicular to the arm. Like if this is, if this is the R vector, this is the R direction. So, and actually this arm is moving this way, it's going down. So definitely the force that push the arm is always perpendicular to the arm in the direction of the theta. So this is P. And here is going to be this way, and here is going to be this way. So it's always in the direction of the theta. So this is P, the pushing force on the arm. Like if we're saying that this arm has a pushing force and this forces keep pushing this arm to go down, so it's always perpendicular to the arm. It's always perpendicular like this way. So to make this arm, I'm not sure if you guys can see my camera. So it's
No,
this
we
is,
can see it.
yeah, so it's always perpendicular to the arm like this. So the R vector is going this way and the theta vector is this way. So the R is always,
Muy establecido, muy establecido.
I think some of you, okay, all right. So here's the arm. Do you guys got it? It's always perpendicular to the arm and in the direction of the theta. Okay.
Yeah, so that makes sense. And what about N?
Okay, so let's think about N. So the N is like is the normal force from the moving mass on the arm. So okay, let's let's get real examples here. I think I have one here somewhere. Oh, let's get it from the textbook.
There's a couple in the lecture PDFs. So if you want to maybe check that one out.
I think there's some here. Let me get in the, okay, so it's cylindrical. Okay, let's find this one. Okay, so here's, for example, if I want to map Let me take a screenshot of this. Okay. So here's, for example, mostly as I said, like if this is the bar, so this is the R direction, and this I can see that theta is moving this way. So absolutely, this is R and this is theta. So that's was no saying R is always in the bar direction and theta is perpendicular to the R in the direction of increasing theta or in the direction of the omega. And actually the omega positive, like omega is gonna be positive if you have the right hand rule. If it's returning this way, like this way, counterclockwise, and your finger is towards you, this is positive. If the finger is going this way, so this is negative. This is how I put the sign of the omega, because this is very important when we put it in the problems. So omega here is positive and it's going counterclockwise. So theta is this way. So let's put the tangent normal. So to put the tangent normal is going to be, for example, I know that my body's moving this way. So this is the tangent and this is the normal. I said that B is going to be always in the perpendicular to the arm in the direction of the theta. So this is the P direction. Like if like there's a pushing force, so it's going to be, let's say F or B. And as you can see, it's put down here, like here in the textbook, it's down here. So it's the same like what I put it, but I put it this way. All right, so this is F. The normal force is always in the direction of the n hat. If I have a surface, like if I have a curve, something like this, and my point is moving on the surface like this, so I have this. This is the tangent, and this is the normal. Let me put the tangent better. This is the tangent. This is the normal. So the normal force is something like this, always perpendicular to the surface. And what is perpendicular to the surface is the n hat direction. Same thing here. It's always perpendicular to the surface. So this is n. So for any example that you have, like I have a one from the lecture, and we had like an arm or something that is moving this way, and this is theta, and it's moving this way. So if you want to put tangent normal, let's put R vector reversed. So this is R, and this is theta. And the tangent normal, okay, so this is the tangent. Look at the normal. The normal is like this. So let's map B and theta. B and theta, so theta, let's put P variance. B is something like this. So this is P, because it's always in the direction of the theta. This is the pushing force on the arm, perpendicular to the arm, and in the direction of the theta. Oh my God. It's very slow here. And let's actually change the colors. Let's make it something like this. All right, so this is the theta. So B is this way. And n, can you see the n hat vector? So n is going to be something like this. It's in the in-hat direction. It's the force that coming from the surface. Same thing if you have a body here. So it is coming from the surface down and going to the body. Same thing from the surface and then going down to the body. Did you got it?
Yeah, it actually makes a lot of sense. Now I can imagine it. So it's
Yeah.
pretty not it's not that difficult to draw in.
Yeah.
And then
Same thing.
this is like these problems would usually be including like kinematics and kinematics, right?
It depends. Like, for example, sometimes if I give you distance and time or velocity and time, so that means that like I need you to do some kinematics to drive acceleration and use this in the kinetics with Newton's second law.
Mm-hmm.
But sometimes in the problem, I don't like want you to get into more kinematics and I test you in the kinematics alone, but sometimes I have to mix them. So whatever, if it's both, if I give you distance and time, so definitely you might need to use the distance and time to get velocity and use the velocity to get acceleration and then use the acceleration in the kinetics. You
Yeah.
know what I mean?
Yeah, I do.
Because sometimes I don't have to give you the acceleration directly. I can give you distance and time. Once you have distance and time, you can get velocity. And once you have velocity, you can get acceleration. Once you have acceleration, you can use it in the sum F equal ma. So you need to train yourself on this type of problems. I believe I have some in the notes.
Yeah, I went over them. I saw them. Yeah, it makes sense. I mean, it's like a procedure, you know, you get used to it, you start from there and then you get to there. But I get it. Like if you gave us acceleration, then there's no need to do the
Yeah,
first part.
because mostly in the Newtonian kinetics, we need acceleration. We only need the velocity when we have the a normal, like something like this, an, because an is equal v square over rho. So somehow you need to get the velocity.
Mhm.
Okay. So, and you need also to be able to distinguish between the normal acceleration and the tangent acceleration. The tangent acceleration is the rate at which a body is speeding up or decelerating, accelerating or decelerating. But normal doesn't have anything to do with the speeding up of a body. It's always depends on the velocity of the body and the radius of the curvature. Yeah. All right. So does anybody have any question related to this problem? We have talked about it like for 15 minutes now. So I believe the most important part is to be able to map the coordinate system. Once you do them, so it will be very easy. And actually the problems of the polar coordinate system is very easy. It's always like if I give you r always function in theta, so all what you have to do, some differentiation, you get r dot, r double dot, and then somehow I will give you in the problem theta dot, and tell you that theta dot is constant, so you have theta double dot. So you need to get theta dot, theta double dot, r dot, r double dot. And once you have them, you substitute in the equations in the equation sheet to get the AR and A theta, and that's it. The problem is done.
Yeah, these are really simple, Professor. I think the only place where you're prone to make mistakes is when deriving R because of like chain rule and product rule.
Yes, yeah, that's why you need to familiarize yourself with the differentiations and all these stuff here. You mean like get r dot and r double dot?
Yeah, because it's like look at R dot, you have to like differentiate 3 sine 2 theta and then like yeah, it's not like you just because if you just differentiate it, you get dr, which is different.
Yeah, and also I need you to keep attention to like 3 sine 2 theta. So when you get r dot, it's completely different if you get dr d theta. R dot is dr dt. But when you calculate xc, so xc is r over dr d theta. So let me also emphasize on this, dr d theta. Sorry. Okay, just 1 minute, guys. I'll be back. I'm back. So the thing is that I want to emphasize on now is like just some of you, if he's is not familiar with the differentiation rule that we've been talking about. So let's solve an example here. Like if, for example, r equal to 3 sine 2 theta, and you want to get dr d theta, this is going to be 3 cosine 2 theta multiplied by the derivative of what is inside the sine. So the derivative of 2 theta with respect to theta is going to be 2 d theta over d theta. And this is equal to 1. But if you gonna differentiate this with respect to t, so this is gonna be 3 cosine 2 theta multiplied by d theta 2 d theta dt, because you differentiate with respect to dt, not d theta. And this is not equal to 1. This is equal to theta dot. So pay attention to this. And this is going to be 6 cosine 2 theta. So this is very, very important. Okay, let's get back. All right, so this problem. Does anybody have any question in the third problem? So this problem is just to have some like geometry, like you need to calculate, for example, the angle, the angle theta. So here, like this theta and this theta, so that you can do some velocity analysis, but it's completely like straightforward. Once you get V, everything's gonna be straightforward. But if anyone has any question, we can solve it. Okay.
Yeah,
So here it's
Professor, can
saying,
you?
yeah.
I heard like you're my TA. I don't even, but he's like literally doesn't come.
Okay. Does any of you have any question related to the problem? Marvin, you were talking.
Like he's just a tutor. I don't think he. I don't know. You gotta
Yeah,
put the
I was
music
just
over
wondering,
there.
can you pass
Probably
over this question? Because I'm not sure about this one.
Okay.
I don't know.
Carrie, there's some background noise from your end.
You know what?
I apologize, Professor. I was gonna say the same thing as Marvin, sorry.
No problem, no problem. Just, okay, yeah. Okay, so here it says a marble with a negligible mass travel, like this small ball travels on with a constant velocity. So I told you constant velocity, so that means that the acceleration and not the whole acceleration is equal to 0. So when I say constant velocity, that means the tangential acceleration is 0, not the whole. Okay, let me. Screenshot from the problem. So it says here that the velocity is 10 centimeter per second. And what I'm asking for, okay, along a quarter of a circle pass radius is for 15 centimeter on a horizontal surface. When the marble is at point B, determine the velocity vector in XY coordinate system. Okay, that's fine. So to determine, so I know the location of my body. It's here. So what I want to do, I want to get actually the angles here that the velocity has at this location. And to do this, I need to find this angle. If I found this angle, I know that this and this equal to 90 degrees. So let's take this body out. All right. let's say that we have this circle, and actually it's not a full circle, but anyway, let's here, and I know that my body is somewhere here, and this is the velocity vector v, and I'm given that this distance is 12 centimeter. If we go up, this is 12.5, and this is 15 centimeter radius. So what I want to do here, I want to get this angle, because if I have this angle, I will be able to get the velocity components. I will be able to get this component and this component, because I will be able to know what is the sine and cosine. Okay, so I know that this angle and this angle is 90 degrees. So absolutely this angle is equal to this angle. So getting this angle, so you will have cosine theta is going to be equal, let's name this as theta. This is going to be, cosine theta is going to be 12.5 over 15. And then you can get cosine inverse and get what is the theta. Or you can get the other angle, like the one in the model answer. The one in the model answer, that's what I did. Here, I get the other angle. And the other angle is going to be the sine. Like looking here, I get the other angle, and then theta is equal to 56.44 degree. So it's going to give you the same thing, but my way is going to give you theta, which is 90 minus 56 degree, which is going to be like 33 degree or 34 degrees. So it's going to give you like same thing. So somehow you are going to get theta here as like 33 degree or 33 point something. But my model answer is going to give you the other theta, like it's going to give you, let's name this phi. It's going to give you this angle. So both way are fine. Like if you got phi, so this is 12.5. So sine phi is going to be equal to 12.5 over 15. Same thing. So once you get theta, so you know what is this. So you can get the velocity Vx is going to be V cosine theta, and Vy is going to be V sine theta. And then you get the x and y component of the velocity. Like the same way that I did it. And then you get Vx and you put it in the I direction, and Vy you put it in the J direction. So this is the first requirement. The second requirement, determine the velocity vector in tangent and normal. So that's a very, very easy question. Why? Because I know from Versta principle that there is no normal component for the velocity. All the velocity is always in the tangent component. So if I mapped the tangent normal coordinate system, I know that the tangent is in the direction of the velocity and the normal is to the center. So the velocity, the whole V is in the tangent direction and 0 is in the n hat direction. So if the velocity is, if the velocity, given velocity is 10 centimeter per second, so this is going to be 10 in the tangent direction plus 0 in the n hat direction. I believe the last requirement is determine the acceleration in tangent normal components. I give you in the problem here that travels at a constant velocity. Once I say constant velocity, that means the body is not accelerating or decelerating. So that means that the A tangent, which is equal to dv dt, and I know that v is constant, so A tangent is 0. This will leave me with getting the A normal, and A normal, it only depends on the velocity v square and rho, and that's very, very easy because I know that the velocity is equal to 10 and the rho is equal to 15, so I can get 100 over 15. Once I get it, so this is gonna give me here 10 squared over 15, 6.6 centimeter. So the A acceleration is 0 in the tangent and 6.6 centimeter per second square. So this is how I can get the the normal acceleration. So keep in mind, normal acceleration doesn't depend if the body accelerating or decelerating. It only depends on what velocity that the body is moving with, which is the one that's given here in this problem, the velocity, and the radius. That's what is the my body depends on. Like it's like imagining that you are like, as I told you in the lecture, that there's a road and there's an exit from the road that you need to take, something like this, and this is the road. Once you get into this exit, all what matters is your speed and the radius of this exit. So once you get here, just to keep yourself on this path, like once you drive your car, there's always pushing that you need to leave the path. You need to like move this way. You need to like move this way. So what keeps you on this track is the normal acceleration, A normal. And this is depend on the velocity v square and rho. Doesn't depend if the body is accelerating or decelerating. When I say body is accelerating and decelerating, so all this is depends on the tangent. It's like taking this curve outside and try to fold it down to make it a linear path, and assuming this car is moving on it as a linear path, and see if this body is accelerating or decelerating. Okay. All right, so that's for the question number 3. All right, let me go to, I have another difficult problem here. Yeah, this one. Does anybody have any question for this problem?
I just wanted, I got like, I understand the first part of the whole problem, the getting the magnitude of total P. Again, like, it's just because last time I asked you, just can you do like the derivative of y? Because once you get the derivative of y, you can get a y dot and y double dot, which is for question 2 and 3. I did it, but just so I make sure that I know how it looks like.
All right, so here y is equal to y is equal to 10. Let me take this problem out.
Professor, would there be a problem similar to this one on the exam?
Well, I can say what is the exam question is, but definitely not this problem.
Like, it won't look like this? Like, you won't be asking for like all this type of stuff on it?
Well, it depends on the problem, but I will give you stuff that you will be able to solve, like in the same level of the homework and the class lectures, but there will be only one long question, like not all of them are, because we only have 1 hour, so I can't ask you to like solve step by step every question. So some of them will be short, some of them will be a little bit of few steps. But anyway, let's focus on this problem. So here we have y is equal to 10 minus 0.1 x squared. Check here, it says vertical slaughter guide moves horizontally. So this one moves horizontally at a constant velocity. Vx is constant, x dot is 15. So this one is moving Vx, which is x dot is 15 inch per second square, which is the same velocity of this particle. A bin P is currently at x equals 6 meters. So you have this one is 6 inches, sorry, and moves along with the guide as confined by the parabolic slotting equation. Okay, draw a kinematic motion diagram of the bin B, include the Cartesian, tangent normal. Okay, and the velocity and the acceleration of B in a tangent normal vector. So I give you this tangent normal. I didn't ask you for the polar coordinate system. But yeah, so here's y dot is always in this way, and then the magnitude of the total velocity of B. So here I give you the velocity Vx, but I didn't give you Vy, which is the y dot. That's why you need to get y dot. That's a thing. And here the magnitude of, yes, here I'm asking for the magnitude of, well, here the magnitude of the total velocity. You need to get Vx, Vy, and then get the square root of both of them, like this way, like using this triangle. And then the magnitude of Vy or y dot of V, so that's, you need it definitely. And the magnitude of A, Y, which is the y double dot. Okay, so let's actually map it here. Okay, so this is X and this is Y. If we tangent normal, as soon as this is the velocity, it says it's moving this way. So that body is moving down. So if I want to put the tangent is going to be something like this, tangent, and the normal is going to be perpendicular, something like this. This is the normal. So this is how I map the tangent normal. I didn't ask for anything related to polar coordinate system. All right, so that's the Cartesian, and also I'm done with this part. So here's asking for, want me to map the velocity and the acceleration of B in tangent normal vectors. Okay, so let's do it. It's loading here. So I said constant, so definitely there might not be acceleration in the other direction since the velocity is constant. Okay, here it's loaded. Right, so all right. So the velocity is always in the tangent direction. So I'm pretty sure that this is the velocity vector, V. And it's always tangent. So for the acceleration, I'm always having a normal acceleration, an vector this way. And if there is a tangent acceleration, it should be in the tangent direction. But here I can find out that this body is moving with a constant velocity. So that means there is no tangent component. But we will see if that's true or not. But let's, as soon as like I have Vx of this point, because it's given here. The Vx is given here. So let me write it in red. So I know that Vx is positive and it's going this way. This is Vx. So what I'm interested in right now is Vy. This one, Vy. I don't know it. So Vx is equal to which is x dot 15 inch per second. Okay, so Vy is going to be y dot. So getting y dot, I need to differentiate this with respect dy dt, not dx. So this is 0.1. Okay, so the differentiation of 10 is going to be 0. The differentiation of 0.1 x squared is going to be 2. And I have negative outside, multiplied by 0.1. And this is going to be x, multiplied by the derivative of what is of x. So it's going to be dx dt, which is x dot. So this is going to be negative 0.2 x multiplied by x dot. So 0.2, and actually he said that the body as at x equal to 6 inches, so we can substitute at x equal 6 inches because this is our origin. And then x dot is given 15 inch and it's constant. So if you want to get it, it's going to be 0.2 multiplied by x, which is 6 inches, multiplied by 15, which is x dot, and then you can get it. And I believe this is what is in the model answer.
Yeah, it's negative 18.
Yeah, where is it? Y dot. Hmm. Okay, so did he got V first? Oh yeah, here's Y, and then the slope. Did I got it somewhere here? It says 1510 theta, but do we have V total?
Yeah, we calculated that first. For B1, we were supposed to get the total, and then we used the total to calculate, you could use the angle and the total to calculate Vy, or you could use the equation itself like you just did.
So I believe, yeah, all of them is going to be right. So the velocity, the magnitude of the total velocity at B. So once you have both of them Vy, you have, for example, Vy and Vx. V is going to be the root of Vx squared plus Vy squared. So I got Vy and I already have Vx, so I can get them. Okay, so this is the magnitude of the total velocity, the magnitude of Vy. So this is the one that I got it here. And the last one is the magnitude of Ay. So the thing is, I need to get the total acceleration where it is so that I can get Ay, or I just get the second derivative of y. So I have already y dot is equal to y dot is equal to negative here 0.2 multiplied by x multiplied by x dot. So I have two terms to differentiate here. So y double dot is going to be the derivative just want to change the color. Okay, yeah, so the derivative of this part first, so this is going to be negative 0.2 multiplied by dx dt, which is x dot, and then we have another x dot, so this is going to be squared, plus negative 0.2 x, let's put negative. Negative 0.2 x dot square, and this is going to be plus, but I already have negative 0.2 x, so I'm going to put negative 0.2 x as it is, and then I'm going to differentiate x dot is going to be x double dot. So I already, like, if you substitute with the variables that you have, so this is going to be negative 0.2, and x dot, it's already given, which is Vx. I believe it was 15 here. Vx, which is x dot, is given 15. I already have x, but also is given that it's a constant velocity. So that means that x double dot is 0. So the term that has x double dot should be 0. This one, and you only have this term. So it's going to be negative 0.2 multiplied by 15 all square, and then you get all your y double dot. And I believe this is the same thing here in the model answer. So you have y dot, and then here, yeah, can you see? But x double dot is going to be 0. So you only have negative 0.1 multiplied by 2. So it's a negative 0.2 x dot square. And then you will be able to get y double dot, which is a y. Does anyone of you have any questions? So yeah, go ahead. But just one second, I just want to wrap up. Like, look at this question is the way, like, once you see something like this is the point. So right away, as I did it in the problem. Here, I just get the x, get the y, and put the tangent, and put the tangent and put the normal, and I identified how my coordinate system looked like. I give you an equation for y and x. So since I give y and x, so you will be able to get y dot, y double dot, so you know the velocity in the y direction, the acceleration in the y direction. I give it to you in an equation form. However, on the x side, I give you x right away. I give you x is 6 inches. I give you x dot is 15 inches. And I told you information that is constant. So x dot is equal to 0 since I gave you that the Vx is constant. So I give you all the information about the velocity and the acceleration as a y, y dot, y double dot, x, x dot, x double dot. So you have all this information. So you will be able to get all this stuff. Just think about it this way. Everything's given. I give you one of them as an equation so that you can do some differentiation, and one of them direct here and here. And I told you it's a constant, so it's here. So it's all about how you translate the text of the question. Okay? All right, so yeah, go ahead.
For this problem, the acceleration was a -45. On the exam, if we don't put the units like inches per second squared, would you knock off points?
Yeah, maybe 1 point or something, but you are not gonna be chopped like lots of points. Because
Okay.
you need to put the units, yeah, definitely.
Okay, and also if we're
And I'm
doing
not gonna test in the units, like I'm not gonna do that much like, hey, this is mile per hours, and this is like the way that I did in the verse homework. The verse homework is just like to refresh your memory a little bit, but in the exam is gonna be consistent units.
so we won't have to convert.
Yeah, you will not have to convert that much. If you conversion, maybe centimeter, meter, but not miles to meter, not slug to kilograms, stuff like this.
Okay. Also, during the exam, like if we have like a bunch of the work right, but we just like do a miscalculation,
credit.
will you do partial credit?
Yeah, there will be partial credit, absolutely.
Okay.
Yeah. So, okay, let me check the chat. If the exam features any pulley system, will it be similar? Yeah, if there is a pulley system, it will be similar. There will be nothing crazy. Like even the quiz, I give you something to like more to think about it. Like the quiz wasn't straightforward, so definitely it's not gonna be as much harder than the quiz or the problems in the class. Yeah, okay, so we are right now on the top of the hour. We have 10 minutes, so we need to use it properly. So let me get to the point with you guys. Does any of you have any specific questions related to the class, the quizzes, the midterm tomorrow, as I told you, chapter 12, chapter 13?
Professor,
Yeah, go ahead.
is the exam gonna be on paper? Right?
Yeah, I'm gonna
Okay.
give you a paper and I will give you a space under each questions to put your answer.
And we provide our own the sheet, right?
Oh yeah, you will have to print your
Or
sheet. I'm gonna print some. I didn't print them today, but maybe in the morning before the exam, I'm gonna print some if you missed it, but I'm not gonna
Okay.
print the 65 sheet.
Okay, thank you.
Okay. Sure.
Professor,
Yes,
when you
I can't hear you. The sound is like very far away.
can you hear me?
Okay.
Yeah, when you talk about dependent motion, about the question about how it might be similar to the test, you're talking about quiz 2, correct?
Yeah, quiz 2 was kind of like has a trick, like because you have two fixed datums, not
Yeah, and
like
we have to get two different
yeah,
equations.
but
Something
definitely
like
it's not gonna be harder than that. Like it's gonna be like if there is, it's gonna be
okay,
like
thank you.
Professor, I was gonna ask, other than the quiz problems, do you think practicing the textbook problems will help?
okay, so let's put priorities here. The first thing that you need to comprehend very well is the lecture notes. once you comprehend the problems in the lecture notes and everything, the next level is to check the quizzes, like the problem in the quizzes, how they look like, and everything. Then you check the homeworks, you make sure that you understand the problems, but with this limited time, you only have a few hours. So what I do, I go, because you should have done this before. You shouldn't have waited to me to say it right now, but you should have done this before. But at this few hours, what I said is that you make sure if you pick any random problem in the textbook with medium, let's say medium difficulty, that you will be able to think through how to solve it. Like you will be able to map the coordinate system. You will be able to put the Newtonian equation, either tangent normal, r theta, or either x and y. You should be able to do this on your own. If you pick a problem and you will not be able to put your way through the problem, so there's something that you need to go back and revise. So that's what I do if I have a few hours before the exam. What, like sometimes some of you, okay, I'm gonna revise everything and yeah, if you have a lot of time, do this. But right now you only have 6 hours, 10 hours, whatever, when you will sleep. So all what you do is that you make sure that you can work, that you can think through the problem. Like maybe don't solve the problem to the end. Like pick any problem like from chapter 12 and then try like problem that doesn't have an answer. Try to think through the problem. Were you able to put the equations that takes you to the answer? You don't have to solve it to the end. Move to the next problem from chapter 13. Pick a problem and then were you able to understand the idea? Oh, this, I need to do some kinematics to get acceleration. Once I get acceleration, I'm gonna substitute in some of fx, some of fy, or some f tangent, some f normal, some f theta, fr, whatever the coordinate system that you have in your problem. And if you were able to do this, that means that you were able to think, because it's not about you memorize problems in your head, because you are not gonna be given the same problem. You are gonna give different problem. Maybe it's easier, but maybe because you haven't seen it before, maybe you will not be able to solve it. So that's why I want you to train yourself on the thought process. Can you think what is the requirement from this problem and work your way to solve it? That's what you want to do right now. Like not you don't have much time right now, because you should have done this, that you revised and did everything. So right now is to test yourself that you understand the concept and you can apply it on any problem. That's what you need to make sure in the next 6 hours. If you were able to do this, I believe you will do great in the exam.
Thank you so much for the advice, Professor. Will do. Thank you.
Thank you, Professor.
Good luck, guys. We have
Thanks so
5
much,
minutes.
Professor.
If you guys are done, that's fine. But I'm still like but if any one of you have any question, I can't answer it. We still have like a few minutes.
Will you upload a recording of the Zoom meeting
Right
online?
now. Yeah, right now. I
Okay.
will. Okay, it was nice meeting you guys, and I hope you good luck. And with the exam tomorrow, just study well, do your best, and you will do great. Okay.
Thank you, Professor. Have a great
Thank you,
night.
Professor. Have a good night.
Professor, I had another question about can we expect a spring on the test?
You can expect it, yeah. Because
Yeah,
I
okay.
did the lecture, yeah, absolutely. Yep. Okay.
Have a good night, Professor. Thank you so much.
Good night, guys.
Thank you. Thank you.
Thank you. Bye.
Thank you, Professor.